As it was mentioned, I would like to give today a presentation of my group's recent activities in applications of lasers for energy storage, in particular for green hydrogen. This research takes place in FORTH, which is the Foundation for Research Technology in Hellas. We had recently a meeting of the Laser Lab Consortium in our establishment. As you can see in this picture, typically every year this time FORTH looks like this, but this was in the good old days, and unfortunately this image becomes more and more scarce, and this is actually one of the reasons that people, a large community globally is doing a lot of research and spending a lot of effort in applications in energy matters and in environmental matters and so on. So exactly this is what I'm going to talk to you about, the application of my research in energy storage applications. And if I wanted to put a more specific title in my research, I would say that I'm going to present you our activity in enhanced hydrogen production through alkaline electrolysis using laser nanostructured metallic electrodes. This is the result, the combined efforts of two teams, a team at FORTH that I am leading, and I have to mention the team in our partners in our collaborating university, the Technical University of Crete. And we are doing the laser processing, and they are doing the electrochemical analysis. As I said, there is a large community, and there is a lot of global concerns about energy coming from fossil fuels because of its environmental footprint. And of course, as you all know, the last few years, because of geopolitical and international reasons and tensions that arise, focused on territorial disputes and so on. And that's why the community is more and more turning towards primary green energy sources, such as energy coming directly from the sun, or from the wind, or from waves, or even lately there are a lot of very interesting results from fusion power and so on. In any case, the main advantage of these power sources is that they are abundant. However, the disadvantage is that they are intermittent, meaning that they strongly depend on the local climate and the local weather conditions, and that we cannot have these power sources on at any time that we wish. And the proposed solution, or one of the proposed solutions, is when we have the availability of these energy sources to convert the excess energy that we do not use in other chemical forms. And one way is to convert it to hydrogen. And hydrogen has a few strong advantages. For example, it is clean, it has zero carbon emissions, and it has a high gravimetric energy density, and basically, practically anybody can produce hydrogen, which is a very strong advantage. However, there are still several disadvantages of hydrogen, and this is that storage is still a challenge because it is very expensive, and also hydrogen has a low volumetric energy density. Nevertheless, there are several advantages and several uses of hydrogen in both the mobile and the stationary sectors. In the case of the mobile sector, we may have fuel cells or even internal combustion engines giving power to automobiles. Especially lately, there are a lot of premium automobile manufacturers that focus on internal combustion engines that use hydrogen as a fuel. So we have applications in the transportation sector, in the shipping sector, or even for city buses, or drones for military or the security sector, and so on. And also applications in the stationary sector, for example, in industry for direct production of power, or for production of useful chemicals such as ammonia or other synthetic chemicals, fertilizers, biofuels, and the list may go on and on. Hydrogen can be produced through water splitting, and there are several methods of splitting water. For example, the proton exchange membrane or the alkaline electrolysis. Lately, there are advances in solid oxide electrolytes. We have the thermochemical method of splitting water, and also photocatalysis. But I'm going to focus on the alkaline method of water splitting. In the alkaline electrolysis method, we have basically an electrolyte, and we dip two electrodes in the electrolyte, the anode and the cathode. And these are separated by a semi-permeable diagram. The electrodes are connected to a power supply, to a voltage, steady state voltage. And then at the position of the cathode, we have electrons helping water molecules to split into hydroxyls and hydrogen gas. Hydrogen gas, which is the most useful gas in our case, is directly collected. And the hydroxyls, they pass through the semi-permeable diaphragm, and at the position of the anode, they convert to molecular oxygen, which is also a very useful gas, especially when it is pure. And it replenishes the water molecules, and it gives back the electrons so as to complete the circuit. So one of the questions that may arise is how to further increase the efficiency of such devices. And one solution is to, of course, to increase the surface by keeping the volume small. How to do it? There are many laser guys, I guess, among us. We are the consortium of Laser Lab. In Laser Lab, there are several groups that are specializing in laser interactions with matter, and also in laser material processing. So we know this method is well established of using lasers in order to structure surfaces. So in our case, we employ a relatively simple experimental setup where we use a laser beam in order to focus on the electrode surface, the metallic surface. And using these lasers, we end up in surface nanostructuring, and essentially we end up with an effective surface increase. So now we'll start a small parenthesis in order to say a few words about the background of laser matter interaction, and in particular in laser surface nanostructuring. So consider that you have one laser shot shining onto a metallic surface, or any surface in general. So if the energy is enough, we have the removal of material from this surface, and a shallow crater formation is in this case, as you can see in both the SEM images and the AFM images. And this is confirmed also by the intensity cross sections, and when we look at the profiles of this interaction. When we shine more than one pulse on the same surface, then we have a very interesting phenomenon. The second laser pulse falls onto the heavily structured surface, the rough morphology of this surface, and there is a wave scattered that travels along the material surface, the surface plasmon wave. And this surface plasmon wave interferes with the laser pulse itself, which originally created and excited this surface plasmon. So the result of this laser plasmon interference, taking of course into account the wave calculus, this interference leads to spatially periodic distribution of various quantities such as energy, temperatures, carrier densities, hydrodynamic quantities, and so on. And as you can see by this simulation profile that was provided by my colleague George Tsibidis, who has done a lot of work in simulations of these interactions, we have the creation of this interference interference fringes. So when we look experimentally at the result of the this irradiation of several laser pulses on a metallic surface or in a practically inertial surface, we have these ripples appearing that have orientation perpendicular to the polarization of the laser field, and this is also confirmed by the AFM images. And as you can see clearly, this intensity cross-section, this periodic profile here, which has a period that is slightly less and slightly smaller than the period of the laser wave, and it follows practically the period of the surface plasmon. In order to give an overview of the mechanisms that one has to take into account in order to have a good description of all the mechanisms that take place following the irradiation of surfaces. So first we have the laser plasmon interference, which results in a spatially periodic energy absorption on the surface. And then after this, we have energy dissipation mainly via electron transport and electron-phonon interaction. These are two competing mechanisms, with electron transport tending to take energy away from the irradiated surface and into the bulk. And the electron-phonon mechanism tends to localize the energy at the vicinity of the irradiated surface. After some time, and provided that the energy of the laser pulse is enough, we have lattice heating and melting and even evaporation if the energy of the laser pulse is very large. And of course, one needs to take into account hydrodynamics in order to describe the particle flow and capillary wave formation. And after a long time, by long I mean time in the order of nanoseconds or microseconds, we have the lattice eventually cooling down, and we have the surface resolidifying, and we end up with a surface which is micro or nanostructured. In the past several decades, there are several groups that have dealt with the description of these phenomena, both theoretically and experimentally, and our group also has done a lot of work in order to provide up-to-date descriptions of these mechanisms. So after this parenthesis, I would like also to mention that we can have extended large area ripple patterning if we scan the surface below the laser beam in large areas, meaning several centimeters square. We can have a large area that is patterned this way. And also something that I did not mention, but this is another story and I will not go into detail in this presentation. We can employ also temporal pulse shaping in the form of pulses, double pulses with a delay introduced in these pulses in order to switch and tune the morphology and the period of these ripples that are induced on the surfaces in an effort to tune them for applications such as scaffolds, for tissue engineering, or for optical surfaces, or for surface sensors, and so on. Following this, as I said, closing this parenthesis and going back to our problem, which is the increase of the efficiency of these electrodes, we apply lasers on these electrodes in order to increase their surface by fabricating basically ripples and structures in these surfaces. We do this by employing these laser nanotexturing setups at FORTH, and our partners in the Technical University of Crete, they employ the custom-made electrochemical setups in order to provide electrochemical analysis and electrochemical characterization of the fabricated surfaces and actual measurements of the hydrogen produced by these samples. Routinely, in our experiments, we provide and we prepare three kinds of samples. The first one on the left is traditional flat nickel electrodes, and we use them as reference electrodes. And also, we shine the laser beam on these electrodes, and we create a ripple patterned electrodes as a first step of preparation. And additionally, as a second step of fabrication of these electrodes, we further electrode deposit nickel nanoparticles on these metallic electrodes. Let's have a look how these samples look like at the SEM microscope. On the upper hand of this figure, you can see the typical periodic pattern, the so-called ripples. And on the upper right side, when we zoom in, we can measure the period of these ripple patterns. And so also, if you can notice, there are several nanoparticles that are distributed all over the surface of these samples. And by analyzing the intensity profile, we calculate the effective surface to be increased by as much as 15 times. And for the second class of samples, the electrode deposited samples, this is how the SEM micrographs look like. When we zoom, and as you can see in the lower right corner, this structure is a rough morphological structure, and it looks like a dendrite or a neural network. And this is a very rough morphology. And essentially, this network, this neural-like network, smears out the periodic structure that was initially created by the laser interaction, the laser surface interaction. And without any further detail, I'm going to show you now in this slide the most important results that we have, which is the actual hydrogen production when using these electrodes in our electrochemical devices. On the left, you can see the hydrogen production rate versus time. And as you can see here is the black curve shows the performance of the flat surface for comparison. And with green, we can see that the laser nanostructured electrode performance is increased significantly. And with the black curve, we can see that the further electrode deposited and laser nanostructured electrode has the maximum performance in the hydrogen production. It is the production is increased by as much as 5 times when compared to the black curve, which represents the performance of the pristine surface. Similar observations can be made when looking on the right on the cumulative hydrogen production, where we can see that indeed we confirm the first result that indeed with every step of processing of the metallic electrodes, the performance in gas production increases more and more. Also, typically in our results, we also do electrochemical characterization. And as you can see with the cyclic voltammetry on the left, when looking at the current density, that is produced by the metallic electrodes versus the applied potential, we can see with the blue curve that, with the green curve and with the blue curve, that with every step of nanostructuring, we have more and more production of current density. So the behavior is becoming better and better. The same thing is observed when looking at the overpotentials and the Tafel slopes here. And also, a very important observation is when looking at the overpotential performance at a stable current. We see that for the case of the nanostructured electrodes, the overpotential is decreased. And this is very significant because the overpotential is basically a number that characterizes the performance of the whole electrolyzer. So the lower the value of the overpotential, the better the performance of the electrolyzer is. Because the overpotential is essentially the excess potential that one has to apply above the value that is thermodynamically expected. So in order to start the hydrogen producing process. So the less the excess voltage that we need to apply, the better the performance of the electrolyzer. Also, when looking at the double layer capacitance, we can see again that the laser nanostructured electrodes behave much better than the flat electrodes, which means that this result is makes these electrodes makes these electrodes very interesting for applications in supercapacitors. Also, the stability, the performance of these electrodes over time is very important when thinking of applications. Here we have examined these electrodes for the period only for a few hours, but even when testing these electrodes again, several months after their fabrication, we found the same performance. So this is also a very important result. So concluding, I would like to say that we observed increased effective surface area after laser irradiation of metallic electrodes. This is an effect, the field effects. This is an effect that I didn't discuss. However, along with the increase in the effective surface area, we expect also the field enhancement at the nanoparticles that are scattered on the surface to also have their own contribution in the increased performance of these electrodes. This is yet to be examined in our research. Moving on, we observed and measured enhanced electrochemical values, and concluding, we observed a superior hydrogen production performance, which reached the value of 5 times when compared to the traditional electrodes. And also we measured super double layer capacitance, very much increased double layer capacitance, which is important when one thinks of developing supercapacitors. Our research also extends to 3-dimensional structures. In an effort to further increase, to study materials that would further increase the hydrogen production performance. So in this case, we employed pulsed laser deposition, which is another standard method based on lasers in order to process materials. And we used as a substrate a nickel foam, which is commercially available. Basically, it is a sponge like material with it's a heavily porous material, and we shined the laser beam onto a nickel target in order to ablate it and create a lot of nanoparticles that were afterwards deposited on the surfaces of this nickel foam network. This is how it typically looks like when looking at the SEM micrographs. On the left column, we can see the pristine nickel foam in various magnifications. And on the right side, we can see in the same magnifications a film consisting of a lot of nanoparticles that are deposited on the surface of this nickel foam. In this case, it is a film which has a nominal thickness of 300 nanometers, and this is how it looks like. This we have an increased roughness, a much increased roughness in the morphology of this foam. Typically, we develop films of various thicknesses, ranging from 200 nanometers up to 850 nanometers. In the case of the thickest films, the 850 nanometers thick, this is practically not a film anymore, but it is a mixture of cracks and flakes and so on. And when performing electrochemical characterization of these laser-processed three-dimensional electrodes and doing these cyclic voltammetry measurements, we find that there is an optimum in the thickness, in the deposited thickness of these films. And as you can see here, the films with a 300 nanometers thickness experience the best performance when looking at the cyclic voltammetry. Also, the double layer capacitance is increased for the 300 nanometers film, which makes it again useful for applications in supercapacitors. The stability is again very, very nice. And concluding, we have applied and employed basically pulsed laser deposition of nickel nanoparticle layers on nickel foams. And we have found a superior performance in their electrochemical characteristics over the nickel foam, an increased electrochemically active surface area, and also potentials for use in supercapacitors. And although we didn't yet measure the actual hydrogen-producing performance, but we're quite sure because the electrochemical performance is heavily connected, strongly connected with hydrogen-producing performance. We are quite sure that these electrodes are very, very have a lot of potential in producing enhanced amounts of rates of hydrogen. When looking at the future, the near future, I hope, we think of using more sophisticated structures and architectures in order to use them as electrodes in our electrochemical devices. This is one example of one experiment giving this very beautiful picture that unfortunately is not mine, but it was taken by my good friends and colleagues Maria Farsari and Argyro Klini a few years ago, showing a three-dimensional network which also has very dense and very small two-dimensional features. And we expect that electrodes, heavily processed and heavily nanostructured electrodes like this, will have a very much enhanced performance in the application that I have discussed. So summarizing the presentation, we have used direct laser surface nanotexturing and pulsed laser deposition in order to prepare two-dimensional and three-dimensional nanostructured electrodes. We have created a higher surface-to-volume ratio, and we observed this in these structures. One thinks, of course, one needs to think and to consider the interplay with field effects in order to have a full description of the enhanced performance of these structures. We have observed an increased electrostatically active surface area, and of course, the most important observation is that we have measured a superior hydrogen-producing performance of these electrodes. And also, the electrochemical characterization gave us very promising results for supercapacitors. So these electrodes can be used and exploited in order to develop devices with larger capacity in smaller volumes. For the case of military and security and defense applications, we can have stealthy devices and vehicles with no smoke and less noise. In the civil sector, we have sustainable facilities, energy resilient facilities, and thus we can contribute to independence of the European Union from fossil fuels, and globally to contribute to the green energy transition. In terms of technology readiness level, in the lowest technical, in the lowest levels, we investigate physics to further enhance the efficiency of these structures by creating novel nanostructures and architectures, and studying the interplay between important effects such as the effective surface and the field effects that I have discussed previously in both 2 dimensions and 3 dimensions. And to take this story to higher TRLs, we need to team up with material experts. We seek collaborations with material experts in order to provide other components that are essential for these devices, to build prototypes and scale up the procedure. And I would like to finish up with the big picture. A few months ago, in September, if I am not mistaken, the Draghi report that was handed to the chair of the European Union confirmed hydrogen as a key technology and stressed the importance of research and innovation to keep Europe at the forefront. On the other hand, on the other side of the Atlantic, there is a completely different approach by saying drill, baby, drill. So we have basically the clash of 2 worlds and 2 mentalities, at least for the next 5 years. So I think my humble opinion is that this is a time that the European Union needs to come ahead strongly and to take the lead. So I would like to thank all my collaborators for this work, and especially the funding programs, and in particular Laser Lab Europe and the new project Lasers for EU, and of course the other large program, the research infrastructure for accessing nanoscience and nanotechnology. And I would like also to thank you for being here and listening to this presentation. Thank you.